in D block elements, the last class I have told you that the standard reduction potential E naught for metal 2 plus becoming metal, or the standard reduction potential for metal 3 plus becoming 2 plus. Okay, these reduction potential values depends upon I just explain based on this system. It is actually directly proportional to delta H. Okay, it's directly proportional to delta H. Very specifically, the value magnitude is very important. Don't worry about the sign. Okay, the magnitude is very important. As the magnitude of delta H increases, okay, because in while going from metal to metal 2 plus, okay, while going from metal to metal 2 plus, there are many energy involvement exist. Okay, metal to solid to gas sublimation, then gas to dye positive ion, you have two ionization energy potentials, then dye positive ion in the gaseous state to aqueous. Okay, this conversion involves many energies. Okay, so delta H is actually, this delta H is actually it consists of enthalpy of sublimation plus first ionization energy plus second ionization energy, then enthalpy of hydration. Okay, it consists of all these three terms, and out of these terms, last class I have told you that these three terms, okay, is endothermic, right? Endo means the values are positive. These values are positive, whereas the last one, hydration enthalpy, it is usually exothermic, it is negative. So you have positive value and negative value. Okay, usually these three value will be larger for most system. Okay, very specifically in the 3D series, students observe carefully. In 3D series, whatever metal ion M2 plus to M you take, the sum of these three will be greater than the hydration enthalpy. Therefore, delta H is positive for all the metal ions. Students observe carefully. This delta H is positive for all the metal ions. But if you observe the values, that is very important. I'll just show you the values. If you observe the values of delta H, we can calculate delta H, because all these sublimation enthalpy value, first ionization energy value, second ionization energy value, hydration enthalpy values, all the values are available. Standard values, standard enthalpy values are available. Okay, listen, by making use of those values, if you calculate delta H, and delta H comes out as positive. If you observe the value, see, delta H value increases. This is for titanium, then vanadium, like that it increases. For manganese, there is a sudden drop. Delta H value suddenly decreases for manganese. Okay, what is the reason? That we are going to discuss. Then if you come below, listen, copper has the highest delta H. For copper, this is copper to copper 2 plus. For copper to copper 2 plus, the delta H is 921 kilojoule per mole, is very high. Listen, student, standard reduction potential value, okay, is directly proportional to delta H. As delta H value, magnitude of delta H increases, standard reduction potential value also increases. So suppose if I plot for 3D series, student, I am not going to discuss other series. As far as 3D series is concerned, if I plot standard reduction potential for M2 plus ion becoming M versus the atomic number, if you plot from up to chromium, it will increase. Initially it will increase up to chromium, Cr. Okay, titanium, vanadium, chromium. After chromium, there is a small drop drop for manganese. After manganese, then again it increases. Okay, manganese, iron, cobalt, nickel, then copper. Listen student, if you see the values, if you observe the values, all these values, standard reduction potential values, here 0, above all the values are positive, below all the values are negative, below 0, and see all the reduction potentials, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, right? All the values are negative. But for copper, it goes to positive. Then for zinc, again it comes to negative. Okay, this is for copper, this is for zinc. So in 3D series, only copper, that is standard reduction potential for Cu2 plus becoming Cu, right? Or I can say in the other way, Cu becoming Cu2 plus. For this ionization process, Cu solid to Cu2 plus aqueous, for this delta H value, this delta H is maximum. Okay, since standard reduction potential value depends on the magnitude of delta H, and delta H value for copper becoming copper 2 plus, right, among 3D series, if you calculate copper becoming copper 2 plus, for this the value is the maximum value. Okay, since standard reduction potential depends on the magnitude of delta H, so this delta H is very high, therefore it goes above. Okay, so here you expect two questions, three questions actually. Why for manganese the value is low? Suddenly there is a drop, more negative value, okay, compared to chromium. Then why the standard reduction value is positive for copper, and why the standard reduction value is negative for zinc? Okay, three questions are possible from this data. Student, just note down, very important. I'll explain why, what's the reason for this. I just calculated these from the values given in your book. Okay, these data are given, sublimation data, first ionization energy, second ionization energy. Okay, if you calculate delta H, it is very clear that for copper the value is maximum. Delta H value is maximum. It means standard reduction potential is standard reduction potential is directly proportional to magnitude of delta H. Since delta H is very high, so standard reduction potential for copper is very high. Actually, it crosses the or it goes to positive value. Okay, for other metals it is negative, for copper it is positive. Okay, take down student. Now we are going to see what is the reason for this. Okay, let me discuss here. So these are the standard reduction potential values for M2 plus becoming M. I have taken only 3D series here. Okay, scandium is not given because you know very well, for scandium the only possible oxidation state is +3, correct? For scandium the only possible oxidation state is +3. +2 is very difficult for scandium, so I didn't include that. Okay, so here the reduction potential for titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc values are given. Students, observe the values carefully. Titanium minus 1.63, very low. Okay, negative, high value means very low. Minus 1.18, slightly increasing. Minus 0.9, increasing, correct? So from titanium to chromium the value increases. See here, from titanium to chromium the value increases, but in the negative side, right? All the values are negative, right? Among the negative values it is keep on increasing. After chromium, see this, after chromium minus 0.9 the value become minus 1 point, more negative. It is more negative, that means the value suddenly decreases for manganese, right? After manganese again it is increasing. Then for copper it become positive. Why the value is positive for copper? Then why the value again decreases, become negative for zinc? Okay, we need to explain this. Okay, first let us explain why the value is negative for manganese and zinc. For manganese it is more negative, for zinc it is negative. What is the reason? The reason is this, student. Follow this carefully. It's very simple actually. Listen. Students, observe this carefully. If whenever you use standard reduction potentials, it means it is in the aqueous medium. Okay, it is in the aqueous medium, so you should be a little careful in that. So here Mn, manganese, right? Mn2 plus should become Mn. This is called reduction. It should gain 2 electron. It should gain 2 electron and become manganese. Okay. Students, observe carefully. Mn2 plus becoming Mn. This reduction potential E0. Mn2 plus become Mn. Right? If this is positive, suppose, students, observe carefully. If it is positive, what does it indicate? Listen, compared to reactant, product is highly stable. If it is positive, Mn is highly stable. Mn is stable. Okay. Suppose if the standard reduction potential for any species, not only, see, I have taken this example. Okay. This is applicable for any system. If the standard reduction potential is negative, it means the reactant is more stable. Student, here Mn2 plus is more stable. That's the meaning. So for manganese, the value is more negative. What is the reason? Okay, let me write in a separate page. Students, observe carefully. For manganese, standard reduction potential for Mn2 plus become Mn. This value is minus 1.18 volt. Okay, what is the reason why it is more negative? What is the reason? The reason is Mn2 plus by gaining 2 electron become Mn. Okay, since this value is negative, it means Mn2 plus is more stable. Okay, standard reduction potential negative means, students, observe carefully. This is reduction reaction, right? Gain of electron is reduction. In any reduction reaction, if the reduction potential Mn2 plus become Mn, if the reduction potential is negative, it means reactant is more stable. This is more stable compared to the product. That's the meaning. If it is positive, product is more stable. Students, keep this point in mind, very, very important. So, since the reduction potential for Mn2 plus becoming Mn, it is more negative, it implies that Mn2 plus ion is more stable. Now the question is, why it is more stable? You know very well, Mn2 plus ion, the electronic configuration is, outer electronic configuration is 3d5. Outer electronic configuration for Mn2 plus is 3d5. 3d5 is half-filled configuration, right? It is half-filled. You know very well, half-filled configurations and fully filled configurations are more stable. It is more stable. So due to half-filled configuration, Mn2 plus ion is more stable. So it is very difficult to convert Mn2 plus to Mn. That's why this value is negative. Okay? Yeah, students, is this point clear? Any doubt? Hello students, turn on your camera. Hello students, turn on your camera. Students, am I audible?
Yes, sir.
Yes, turn on your camera, students.
Sir, my camera is not working.
What about others? Ashika? Tejasvi? Tejasvi is not there? Okay. Right. Is this point clear, student? Any doubt? Standard reduction potential for Mn2 plus becoming Mn is more negative. What is the reason? The reason is Mn2 plus ion. Students, observe carefully. if the standard reduction potential negative means, okay, if the standard reduction potential is negative means left hand side or reactant is more stable. Remember this, very easy to identify. If it is positive, this is more stable. Okay, for any system, if it is negative, this species is more stable. If it is positive, then this species is more stable. So since this value is more negative, it indicates that Mn2 plus ion is more stable. Why Mn2 plus is more stable? You know very well, Mn2 plus has d5 configuration. Okay, off-filled configuration. Off-filled state configuration is more stable, you know very well. That's the reason why the standard reduction potential is more negative. Is this point clear, student? Hello? Hello, students, respond.
Yes, sir.
Right. Students, observe here, okay, and try to respond here. Yes. Okay, ma. Now, so manganese has more negative value. I have given the explanation. Now the next one is zinc. Listen, student. Standard reduction potential, zinc 2 plus becoming zinc. Okay, for zinc it is minus 0.76 volt. Students, observe carefully. Now you can ask me a question, sir, for copper it is positive. Immediately for zinc it becomes negative. What's the reason? The reason is that, listen, what does this value indicate? Negative sign? Negative sign indicates that, okay, if the reduction potential is negative, it means that Zn2 plus is more stable. That's all. Very simple. Zn2 plus is more stable. So which means zinc 2 plus, by gaining 2 electron, it should become zinc. But since this is more stable, this process is difficult. If reactant is more stable, then this process is difficult. That is the reason why the value is negative. Now, why it is more stable? Why? Because zinc 2 plus has 3d10 configuration, 3d10 electronic configuration, which is fully filled. Fully filled. You know very well, off filled and fully filled configurations are more stable. So this is more stable. Since this ion is more stable, so this process, okay, is very difficult. That is the reason why the value is negative. Note down, student. Note down. Very, very important points. Is this clear, student? Any doubt?
Yes, sir.
Right? Good. Now, so I have given explanation for these two. Why manganese reduction potential is more negative, and why zinc is negative. I have given the explanation. Now the next question is, why does copper has positive value for reduction potential? What is the reason? Students, if you observe the values of the standard enthalpy of sublimation value, first ionization energy value, second ionization energy value, and the enthalpy of hydration, if you note these values, okay, for copper, the second ionization energy value for copper is very high compared to other metals. Okay, students, data are available in your book. You just go through after that. Okay, once the class is over, you just go through. Okay, compared to other metals in the 3D series, okay, copper has highest second ionization energy. Okay, so listen carefully, student. That is Cu plus 1 becoming Cu plus 2. Okay, for this you require very high energy. Very high energy is required. Okay, therefore delta H, total delta H, okay, magnitude, total delta H magnitude becomes very high. Right? And standard reduction potential for copper 2 plus becoming copper, since it is directly proportional to the magnitude of delta H, and delta H magnitude is very high. That's the reason why standard reduction potential is very high. among 3D series. Okay, so very high means it even it actually crosses the negative value and become positive. Okay, that's the reason why the standard reduction value of copper 2 plus to copper is positive, student. Note down. Note down. Very important.
Yes, sir.
Okay, this is another important question. Keep this in mind. Then, so why copper standard reduction potential for copper 2 plus to copper is positive? The reason is very simple. Okay, the second ionization energy value for copper is very high. Because of that, okay, if you sum up all these values, you'll get net total delta H. The total delta H become very high. Since reduction potential depends on the magnitude of delta H, since delta H value is very high, standard reduction potential also become very high. Okay, and it is so high that it crosses the negative values and become positive. Okay, yeah. Is this clear, student? Any doubt? Any doubt up to this?
Clear, sir.
Okay, ma. Good. Now, we have few more questions to discuss. Listen, it was observed that chromium 2 plus is reducing, but Mn3 plus is oxidizing agent. Why? Chromium 2 plus. Reducing means, when you say a species as a reducing agent means, according to electronic concept, reducing agent means, suppose I have some species A. Okay, if this species readily donate electron, okay, if the species donate electron, then I can say that the species is a reducing agent. It is a reducing agent. It is a Ra. Ra means reducing agent. A reducing agent should donate electron. That's very important. What is an oxidizing agent? It is just opposite. And if I say a species as oxidizing agent, say I'll take some species B. If I say this species is oxidizing agent, then it should gain electron. It should gain electron. If a species donate electron, it is a reducing agent. It acts as a reducing agent. If a species gain electron, it is a oxidizing agent, OA. This is general idea. But this is very important point. A species acts as a reducing agent by gaining electron. It means after gaining electron, that A become more stable. Okay, see the species, I'm sorry, if I say a species is reducing agent, after donating electron, that species become more stable. Similarly, if a species acts as oxidizing agent means, after gaining electron, that species become more stable. Clear, student? Now listen, I'll just explain with this example. Chromium 2 plus is reducing agent. Why? It is actually a strong reducing agent. What's the reason? Chromium 2 plus is a reducing agent. Why? Reducing agent means it should donate electron. Yes, chromium 2 plus donate one electron and become chromium 3 plus. Now we need to identify listen, it is a good reducing agent. Okay, it is given clearly chromium 2 plus is a reducing agent. Why? After reducing agent should donate electron. After donating electron, the species obtained should be stable. Yes, this is more stable. Chromium 3 plus is more stable. Why? Why? Listen, what is the electronic configuration of chromium 3 plus? Chromium 3 plus, student, observe carefully. Chromium 3 plus electronic configuration is 3d3. Actually, chromium is 3d5, 4s1. Chromium. Right? From chromium, if you remove 3 electron, you will get 3d3. 3d3 is not off-filled, but in aqueous medium, students observe carefully. In aqueous medium, the 3d subshell, okay, will split into 2 set, correct? Under coordination chemistry, we discussed that. In aqueous medium, these are all reducing agent. It acts as a reducing agent in solution medium, correct? So in aqueous medium, d subshell containing 5d orbital, it is split into 2 set. One is called T2g set, the other one is called EG set. and these 3 electrons, okay, will occupy the lower d orbitals. So 1, 2, 3. Now see, it is half filled. T2G is half filled. That is the reason why chromium 3 plus is more stable. So why chromium 3 plus is more stable? The reason is it has half filled T2G set. Half filled T2G set. T2G set has 3 d orbitals. Okay, it has half filled T2G set. That is the reason why it is stable. Since this is stable, so chromium 2 plus readily donate electron and become chromium 3 plus. So that's the reason why chromium 2 plus is a reducing agent, good reducing agent. Students, observe carefully. I repeat again. For any if I say a species as a reducing agent, it should donate electron first. After donating electron, that species should become stable. Clear? So if I say chromium 2 plus as reducing agent, it means it should donate electron. Yes, chromium 2 plus donate electron and become chromium 3 plus. Chromium 3 plus is stable. That is the reason why it acts as a strong reducing agent or good reducing agent. Is this point clear, student? Hello, students. Is this point clear?
Yes, sir.
Yeah, note down. Then another question,
Yes, sir.
another question is asked here. Mn3 plus is a strong oxidizing agent. Why? What is the reason? What is the meaning for oxidizing agent? I have told you. Oxidizing agent means it should gain electron. Okay, if I say any species as oxidizing agent, I told you. If I say any species as oxidizing agent, it should gain electron. After gaining electron, that species should become stable. Then only we can say that it is a strong oxidizing agent. So in the case of Mn3 plus, students observe carefully. In the case of Mn3 plus, by gaining one electron, it becomes Mn2 plus. Okay, and you know very well Mn2 plus has half-filled configuration. It has half-filled configuration, so it is stable. Mn2 plus is stable, whereas Mn3 plus is not stable. Mn3 plus configuration 3d4, it is not stable. It is not stable. Okay, that's the reason why Mn3 plus readily gain electron, because it is less stable or it is unstable. Mn3 plus is unstable, so it immediately gain electron and becomes stable. That's the reason why Mn3 plus acts as a strong reducing agent. I'm very sorry, oxidizing agent. It gains electron, right? Mn3 plus gains electron. So Mn3 plus acts as a strong or a good oxidizing agent. Okay, take note, student. Is this clear?
Yes, sir.
Right now, take note. Now, then next important point. Yeah, see this question, students. Standard reduction potential for Mn3 plus becoming Mn2 plus is high positive value. High positive. Students, tell me, if the reduction potential is positive, what does it imply? If value is positive, what does it imply? Among the two, which is more stable if it is positive?
Mn2 plus,
That's
sir.
all, very good. This is more stable. This is more stable. Can you tell me what is the reason why it is more stable? Mn3 plus, okay, to Mn2 plus. This reduction potential is positive. This reduction potential is, don't worry about the value. Mn3 plus becoming Mn2 plus, this value is positive. It means, positive means this process occurs readily. Why it occurs readily? Because Mn2 plus is more stable compared to this. Why this is more stable? Mn2 plus has D5 configuration. D5 means half filled. since it has half-filled configuration, okay, Mn2 plus, students observe, Mn2 plus has half-filled configuration, it is stable. Whereas Mn3 plus is D4. D4 is not stable comparatively. Okay, compared to this is less stable. Less stable or unstable, we can say. Compared to this, it is less stable. So this less stable ion, by gaining one electron and become Mn2 plus, that is called reduction. Since the reduction potential is positive, it implies that the Mn2 plus ion is more stable here. Why Mn2 plus ion is more stable? Because of half-filled configuration. Is this point clear, student? Any doubt?
Yes, sir.
Yes, ma. No doubt. No doubt. Now, students observe here. I have given two questions. Cupric iodide. CuI2 means cupric iodide. FeI3 means ferric iodide. These two compounds do not exist. You know very well what is the reason for this. You know very well, for copper exhibit two oxidation state. One is Cu plus 1 cuprous, another one is Cu plus 2 cupric. You know, I have told you already that higher oxidation state for any metal in general, higher oxidation states are stabilized by either fluorine or oxygen. Either fluorine or oxygen. So if it form compound with the fluorine, CuF2 exists. Students observe carefully. CuF2 exists because fluorine is more electronegative. It can gain more number of electron from copper. So copper to copper 2 plus is possible. Whereas in cupric iodide is less electronegative. Iodide is less electronegative. Therefore, cupric iodide formation is not viable. At the same time, students observe carefully. Cupric ion, okay, and we have iodide ion. Iodide ion is a reducing agent. What it will do? It will reduce cupric ion. Therefore, you will get cuprous iodide, Cui. You will get cuprous iodide. It becomes plus 1. Okay, so that's the reason why cupric iodide does not exist. Because if cupric iodide is formed, immediately the iodide act as a reducing agent. It will reduce cupric ion to cuprous. Okay, so what's the point you should keep here is that higher oxidation states are stabilized generally by either fluoride with the fluoride or with the oxygen. Okay, with the less electronegative element like iodine, higher oxidation state are not stable. Same reason applicable here. Ferric triiodide is not stable. Why? The reason is, for iron we have many oxidation state actually. I'll take these two, Fe2 plus, Fe3 plus. One second, student. Right. Fe2 plus and Fe3 plus. This is higher oxidation state. Higher oxidation states are usually stabilized by oxygen or fluorine. So it can form stable compound with the fluorine. Fe3 exists because fluorine is more electronegative. Okay, but with the less electronegative element like iodine, Fe3 does not exist. Because it's less electronegative, it cannot form, okay, or it does not gain more electron from iron atom. So Fe to Fe3 plus is difficult. At the same time, iodide is a good reducing agent. So what will happen if this compound, if at all if it is formed, what will happen? This ferric ion is get reduced by iodide and become ferrous iodide. Fe2 exists, Fe3 does not. Because so this is a general point, student. Higher oxidation states are stabilized by either with the fluorine or with the oxygen. Okay. Yeah. Is this clear, student? Any doubt? Yeah. Good. Now let me move over to the next property. One more information here I like to give. regarding how to compare reducing power of different species. Reducing power of different species. Suppose I'll take few examples, students. 1 second. Yeah. For M3 plus ions, standard reduction potential values. Students, observe carefully. I'll give some reduction potentials for some M3 plus to M2 plus ion of 3D series. Okay, the values are, I'll give for a few elements. Say for chromium, the value given is minus 0.41. Just student observe the values. For manganese, the value given is positive plus 1.57. These values are given in the book. And for iron, the value given is plus 0.77. Okay, now listen student, I'll give some important information here. This is also very important for your examination. Listen, what's the meaning? Standard reduction potential for chromium 3 plus becoming chromium 2 plus. Okay, M3 plus to M2 plus. So chromium 3 plus to chromium 2 plus value is minus 0.41. Okay, students, observe carefully. Chromium 3 plus becoming chromium 2 plus is difficult because the value is negative. It is difficult. Whereas the ulta, suppose I'll take like this, is not chromium 2 plus becoming chromium 3 plus. Okay, I'm just changing the redox system. Okay, I'm changing reduction to oxidation now. Chromium 2 plus to chromium 3 plus is just plus 0.41 volt. Positive means this process occurs. What does it indicate? It indicates that chromium 2 plus by donating one electron become chromium 3 plus. Okay, so by seeing this value itself, we can say that chromium, if the value is negative, then chromium 2 plus act as a reducing agent. Students, observe carefully. Whenever standard reduction potential is negative, then you can say that this species, okay, not this one, this species can act as a reducing agent. So this can act as a reducing agent because the value is negative. Right? Now, similarly, if I take manganese, for manganese Mn 3 plus to Mn 2 plus, the value given is plus 1.57 volt. This is positive. That means this process occur readily. It means Mn2 plus is not a reducing agent, whereas Mn3 plus is a good oxidizing agent. Similarly, if I take iron, for iron, students observe carefully, Fe3 plus becoming Fe2 plus, the value is positive, plus 0.77 volt. That means this process occur readily, okay, not the other one. So that means Fe2 plus is not a good reducing agent. Because the value is positive. So Fe3 plus ion try to become Fe2 plus only. Okay, so what I am trying to say here is, listen student, this is the general trend, student. If standard reduction potential, if it is negative, if the standard reduction potential is negative, then the reduced species, okay, or let me show like this. Suppose if I take di positive ion become metal, if this reduction potential is negative, it means this metal is a good reducing agent. If the standard reduction potential for M3 plus becoming M2 plus, if this value is negative, it means M2 plus ion act as a good reducing agent. If the value is negative, student, the product, this is product can act as a reducing agent. Clear? Is this point clear, student? Is this point clear?
Yes, sir.
Right? Now, sometimes they'll give two or three metals. Listen, suppose I'll give metals like I'm not going to give you the specific symbol of the metal. Instead, I'll give like this. Okay, A2 plus A is a metal. B is also a metal. And I have another species C. C also a metal. Okay, A, B, C are metal. All the values, I'll give the values like this: minus 0.7 volt. This is minus 1.1 volt. This is minus 1.81 volt. Now tell me, students, among ABC, which one acts as a good reducing agent? Since all the values are negative, can you give the answer, student?
A, sir.
Why? Why A? Aditi, observe carefully. All the values are negative, right? All the values are negative,
Sir,
which
C.
means C is the correct answer. Yes. Listen, negative means A. Here A can act as a reducing agent. Here B can act as a reducing agent. Here C can act as a reducing agent. So in all the three, A, B, C can act as reducing agent. But now the question is, among the three, which is a good? See the value which is more negative. See, more negative. Third one is more negative, right? Minus 1.81. Okay, higher or more negative value of standard reduction potential E0 M2 plus becoming M. Okay, implies that M, the metal M, acts as good reducing agent. Take down, student. More negative value of standard reduction potential indicates that metal acts as a good reducing agent. Is this point clear, student?
Yes, sir.
Yeah, this is very important for competitive examination. Okay, keep this in mind. Now, 1 second, students. Got some problem. Right. Okay. So with this we have completed electrode potentials and some related concepts. Now we'll discuss the next important property called magnetic properties. Right, note down. Magnetic properties of D block elements or transition metal elements. Okay, take note, student. You know very well, in D block, the metal, right, as well as the metal ion, or the metal ion carrying some charge, they usually have unpaired electrons. Okay, they usually have unpaired electrons. Students, observe carefully. Unpaired electrons. Usually, not always, usually. If any species, student, note down, if any species contain no unpaired electron, suppose there is no unpaired electron in any species, in any D block elements, then we can say that species is diamagnetic. That species is diamagnetic. If there is no unpaired electron present, then we can say that species as diamagnetic. For diamagnetic species, okay, they are weakly repelled by the magnet. Diamagnetic species are weakly repelled by the magnet. If you keep it in a magnet, they are weakly repelled. That's the point you should keep in mind. If any species contain one or more unpaired electrons, then we can say that the species is paramagnetic. You can say that the species is paramagnetic. Paramagnetic species are weakly attracted weakly attracted by the magnet. Students, keep this point in mind. Diamagnetic species are weakly repelled, whereas paramagnetic species are weakly attracted by the magnet. Paramagnetic species contain one or more unpaired electrons. Then last category, there are some species which contain one or more, in general they contain two or more unpaired electrons. Okay, and these species can be called as ferromagnetic. These species can be called as ferromagnetic, and they are strongly attracted by the magnet. Strongly attracted by the magnet. So what is the difference between paramagnetic and ferromagnetic? Very simple. Paramagnetic, ferromagnetic both contain unpaired electron, whereas the difference is paramagnetic species are weakly attracted by the magnet, whereas ferromagnetic species are strongly attracted by the magnet. Okay. Now, students, observe carefully. Magnetic moment. Listen, if species contain unpaired electron, okay, whether it is paramagnetic or ferromagnetic, if species contain unpaired electron, you can calculate magnetic moment. So, magnetic moment is 0. Let me write. Magnetic moment is 0 for diamagnetic substances. For diamagnetic species, magnetic moment is 0. Listen, student. If any species is diamagnetic, you need not calculate magnetic moment because the value should be 0. Okay. Magnetic moment is non-zero for species containing one or more unpaired electrons. Okay. So if unpaired electron present, if species contain unpaired electron, then you will get some magnetic moment. Magnetic moment usually not 0. You will get some value. Okay, students, observe carefully, student. I am going to give some more information here. Observe carefully. Suppose, listen, student, you know very well, in metal ion as well as metal atom, okay, suppose this is a nucleus and we have outer electrons. Okay, assume that this is outer shell. In outer shell we have electron, and the electron revolves. Right, the electron revolve around the nucleus. You know very well. This is called orbital motion. Electron is moving around the nucleus. It is called orbital motion. Because of the orbital motion, okay, electron creates a magnetic field, and it will give a magnetic moment. Not only that, each electron, okay, each of these electrons, they also undergo spinning. They are not only revolving, they are also spinning. Because of the spin of the electron, it will create another magnetic moment called spin magnetic moment. So students, observe carefully. This mu actually made up of two things. One is orbital magnetic moment, orbital motion of the electron, right? Because of the orbital motion, we will get a magnetic moment. It is called orbital magnetic moment. And because of the spin of the electron also spinning about its own axis, and you will get what is called spin magnetic moment. Okay. If you find magnetic moment experimentally, the experimental value consists of the sum of these two actually. Students, observe carefully. The experimental value is actually the sum of these two. Right. But here I like to give a point. Just note down, student, very important. In the case of 3D series, this is very important for JEE main or JEE advanced like level examinations. For 3D species, for 3D series elements, okay, the magnetic moment due to orbital motion, orbital magnetic moment is quenched. It is quenched. It does not appear. For 3D series elements, the magnetic moment due to orbital motion of the electron is quenched. It does not appear. Then the only magnetic moment possible is spin one magnetic moment. Only spin magnetic moment is possible for 3D series in general. For 4D and 5D series elements, okay, you have to consider both orbital and spin magnetic moment, both will contribute. Okay, students, keep this point in mind. So I am going to consider only 3D series elements now, only 3D series elements. So I am going to focus only on spin only magnetic moment. Is this point clear, student, up to this? Any doubt? Students, any doubt?
Yes, sir.
Yes, ma'am, no doubt. What is the formula for spin only magnetic moment? So I am going to find out only spin only magnetic moment. I am not going to consider orbital magnetic moment, spin only magnetic moment, which I am going to represent simply as mu s. Mu s. How to calculate mu s, spin only magnetic moment? There is a formula available, square root of n into n plus 2. The unit of magnetic moment is Bohr magneton, Bm. Unit of magnetic moment is Bohr magneton. Bohr magneton. Okay, so that's a unit for magnetic moment. And what does this n represent? The n represent number of unpaired electrons present in the system. Number of unpaired electrons. Okay, if you know how many unpaired electrons present in the system, yes, you can calculate spin only magnetic moment. Okay, yeah. Now I'll give some examples and I'll show you how to calculate spin only magnetic moment. Right, students, up to this, any doubt?
No, sir.
Right, ma'am. Yeah. See, I have taken few examples. Calculate spin only magnetic moment of the following species. Okay. Our focus is only spin only magnetic moment, and it is 3D series, so only spin only magnetic moment exists. Okay, first I'll take this example A. Chromium 2 plus. Listen, student, for this you must know the electronic configuration. Right? So what is the electronic configuration? For chromium, electronic configuration is 3d5 4s1. Outer electronic configuration. Chromium 2 plus means you should remove 2 electrons. So remove 1 electron from here, remove 1 electron from here. So 4s become empty. If I remove 1 electron here, I'll get 3d4, correct? So chromium 2 plus electronic configuration is 3d4. And you know very well, d subshell contain 5 orbitals. 1, 2, 3, 4, 5 orbitals. Now we have only 4 electron. So first fill up electron, each orbital with 1 electron. Yes, so we have filled up 4 electrons. Now listen, student, all the orbitals have only 1 electron. This orbital has 1, this orbital has 1, this orbital 1, right? Therefore, each of these electrons are called as unpaired electrons. There is no pairing, everything is unpaired. So we have 4 unpaired electrons in this case. There are 4 unpaired electrons. Okay, so n is equal to 4. So what is the magnetic moment? Spin only magnetic moment equal to square root of, you know the formula, n into n plus 2, Bohr magneton. So put the value 4 here. So square root of 4 into.
Sir, your screen is lagging for me.
What about now? Ashika? Tejasvi?
Sure, yes, sir. It's lagging, sir.
What about now?
Even now it's lagging, sir.
Yes, sir.
Okay, let me just continue and see. So if I put n equal to 4 here, 4 plus 2, 6. 6 into 4, 24. So spin only magnetic moment is square root of 24 Bohr magneton. Okay, square root of 24, what's the value, student? Can you tell me what's the value of square root of 24 roughly?
2 root 6, sir.
Square root of 16 is 4, no? 4, no? Can you tell me in fraction roughly?
Approximately 4.8, 4.9, sir.
Very good. It is approximately 4.8 or 4.9 something, correct? Students, listen carefully. If spin only magnetic moment is given, listen, 4.3.2. Okay, after the decimal point, if any number is there, neglect that number. This after the decimal point, don't round off the value. After the decimal point, whatever number is there, just leave it, and the remaining number will give you the number of unpaired electron. So your system has 4 unpaired electron. That's why the value is 4.8 something. Okay, take them, student. Is the screen lagging again?
So now it's better, sir.
Okay, ma. It comes around 4.89 like that. Okay, take 2. So this is the spin only magnetic moment for chromium 2 plus ion. 4.89 Bohr magneton. Similarly, how to calculate for cobalt 3 plus? For cobalt 3 plus, we'll do it here. Students, can you tell me what's the electronic configuration of cobalt? What is the electronic configuration?
3d7
Very good.
4s2.
Yes, 3d7 4s2. So cobalt 3 plus means
3d6.
3d6. 3d6. Now in d subshell we have 5 d orbitals, 1 2 3 4 5. We have 6 electron now. Fill each orbital with 1 electron. So I have placed 5 electrons. 6 electrons should be paired. Now tell me how many unpaired electrons are there, students? How many unpaired electrons?
4, sir.
Yeah, again 4, correct. So what will be the magnetic moment? 4 point? Am I right, student?
Yes, sir.
It should be again 4.89 Bohr magneton. 4 unpaired electron means 4.8 something, simple. Right? Then third one, Fe3 plus. Yes, student. What is the electronic configuration of ion? Aditi, can you tell me?
3d6.
3D, yes ma, 3d6 4s2. For Fe3 plus,
3d5, sir.
correct? For Fe3 plus it is 3d5. 3d5 means the d subshell should be filled with 1 electron. Okay, 1 2 3 4 5. Yes, we filled 5 electron and all are unpaired electrons, so number of unpaired electron is 5. Can you tell me what will be the value roughly? 5 point? If it is 5 unpaired electron, it should be 5 point something. Can you tell me what's the value roughly? Hello, students?
5.8, 5.9, sir.
Yeah, it should be roughly 5.8. Okay, yeah, good. Yes. 5.8 roughly. So you can calculate, and remember, don't forget to put Bohr magneton. That's the unit. Okay, don't forget that. Right? For nickel 2 plus, students, you just try and tell me. I'll wait. You calculate for nickel 2 plus and try to tell me the value. Got the answer?
Sir, 2.8 bm.
Very good. It consists of 2 unpaired electron, so the value should be roughly 2.8 something. Good. Then, students, I'll take 5 more minutes, then I'll stop. Color of D block metal ions. Okay. Students, observe carefully. D block metal ions are in general transition metal ions. Okay, they show color. Okay, the reason for the color, right? Listen, D block metal ions in aqueous medium or in compound form. Okay, they exhibit color. They exhibit color. The colors are the color. Reason for the color, right? What is the reason for the color? The reason for the color is mainly due to DD transitions. DD transition. Color is mainly due to DD transition, or sometimes it may be due to charge transfer transition. In some compound, charge transfer transition may also occur. But for D block elements, for compounds of D block elements, right, the color is mainly due to DD transition. What is meant by DD transition? You know very well. In free metal ion, suppose if we have some metal ion, transition metal ion, having some oxidation state, in free metal ion means it is in the gaseous state. All the 5 d orbitals have same energy. But when they form compound, or when the metal ion is present in aqueous medium, what will happen? The 5 d orbitals get split into 2 set. Okay, the 3 d orbital comes below. It is called T2g set, and this is EG set. If it is an octahedral compound, now the electrons present in the lower d orbitals, these are all d orbitals, right? They absorb energy from the radiation, very specifically from visible radiation. They absorb visible radiation so that the energy is gained and the electron goes to this d orbital to that d orbital, and this is what we call as DD transition. Okay, electron is promoting from one d to another d, so this is called DD transition. For this DD transition, okay, metal ion absorbing radiation from the visible range. If it absorb from the visible range, then you will get color. You will get color. Students, observe carefully. Usually DD transition, we say that it is forbidden transition. It is not allowed. It's a forbidden transition. Therefore, if at all any color appear due to DD transition, it is because of the it is actually forbidden transition. So the color usually appear with the pale colors, light colors. Okay, if color appear due to DD transition, then the color should be pale colors, pale green, pale yellow, like that. Okay, now students, keep this point in mind. So D block metal ion shows color, right? The main reason for the color for D block metal ion is DD transition, and the charge transfer transition also possible. Okay, but mainly due to DD transition, right? And what is the meaning for DD transition? DD transition means electron promotion occur by the absorption of visible radiation. It goes from one T2g set to EG set. That is from one set of d orbital to another set of d orbital. So that's why it is called DD transition. And whenever color appear due to DD transition, the color is usually pale colors, not dark. Color is not dark, it is just pale. Okay, and student, this is very, very important point. If the metal has D0 configuration or the metal has D10 configuration, in D0 DD transition is not possible. In D10 also DD transition is not, because all the orbitals are fully filled, so excitation does not occur. For the electron to move from lower energy to higher energy, the higher energy orbital, at least there should be some vacancy. Students, if there is any vacancy, then only the electron can be promoted here, correct? Then only it will absorb radiation. If all the orbitals are fully filled, then transition does not occur. So D0 transition, if any metal ion or metal atom has D0 configuration, then it should be colorless. If the metal ion or metal atom has D10 configuration, then also it should be colorless. For D0, D10, it should be colorless, student. Okay, for other cases, DD transition will occur, you will get color. Okay, so here I have given a few examples, student, just observe this. Titanium 4 plus is colorless. Why? Titanium electronic configuration is 3d2 4s2. Titanium 4 plus means you should remove 4 electron. If you remove 4 electron, you will get D0. I have told you D0 means DD transition is not possible. That is why titanium 4 plus ion is colorless in aqueous medium. Whereas titanium 3 plus, remove 3 electron here, you will get 1 electron in D. So now we have 1 electron, so you will get color. What is the color? Color of titanium 3 plus is purple. Student, the color given here is the complementary color. That is color we see. But I have told you under coordination chemistry that the color what we see is not the color that is absorbed. Okay, actually the ion absorbing some color. What we see is only the complementary color. So here I have given only the complementary color. Right. Vanadium 4 plus, student, you know very well the electronic configuration of vanadium is 3d3 4s2. Vanadium 4 plus means you should remove 4 electron, so you will get 3d2 configuration. I am very sorry, 3d1. Vanadium 3d1 configuration, which is blue in color. If you have electron in D subshell, you will get color. Okay, only under these two situations, that is D0 and D10, the ion is colorless. So this is colored. Vanadium 3 plus electronic configuration 3d2, it shows green color. Vanadium 2 plus 3d3 configuration violet. Chromium 3 plus, chromium electronic configuration is 3d5 4s1. If I remove 3 electron, I will get 3d4. Yes, it is violet. Mn2 plus is light green or light pink or pale pink because of D5. It has 5 unpaired electrons. Okay, Fe2 plus is green because it has 3d6 configuration. Fe3 plus is yellow, 3d5 configuration. Nickel 2 plus salts are green because of D8 configuration. Copper 2 plus D9 configuration. Copper plus is D10, student. D10. Zinc 2 plus also D10. Since D subshell is fully filled, they do not show, or there is no possibility of DD transition. So these ions are colorless. Okay, students, is this point clear? Is this point clear, student?
Yes, sir.
Yeah. So listen carefully. For a metal atom for a D block metal ion or transition metal ion to exhibit color, or they exhibit color either due to DD transition or charge transfer transition, but mostly due to DD. Okay. Listen, if DD transition occurs, and for the DD transition, if visible radiation is absorbed, then only you will get color. And for DD transition, usually we will get pale colors. Okay, and the notable 2 points here is D0 configuration, D10 configuration. In these two configuration, DD transition is not possible. DD transition is not possible. It's not possible. Therefore, these two configurations, if any ion has these two configurations, then it should be colorless. Clear, student? Then I have given a few examples here. Just go through that. Okay, I stop here. We'll continue in the next class. If you have any doubt, you can ask me, students.